Assalamu alaikum, dear students. Welcome to the lectures of the quantum mechanics. In this, we will solve problem number 3.23, which is from chapter 3 and its number is 23. The question states that consider a system whose Hamiltonian H is this E 0 minus iota, iota and 0, a two-dimensional 2 by 2 matrices where E is a real constant with the dimension of energy. Find the eigenenergies E1 and E2 of H. It means we have to find its eigenvalues of this matrices, and this will give two eigenvalues because it is 2 by 2 matrices. And the second, if the system is initially in the state psi at time t is equal to 0 is equal to 1 and 0, find the probability so that a measurement of energy at t is equal to 0 yield E1 and Et. Means we have to find the probability of coming energy E1, and second, similarly for the probabilities, find the probability for energy E2. What is the probability that whoever state will be in the E2 states, E2 energy levels at it? Okay, so we'll go to solutions. As usual method, in order to solve this problem, we will follow the well-known procedure of determination, like writing any equation in the secular form, for which determinant of h minus lambda I is should be equal to 0, and you know that h is given matrices, lambda is the eigenvalues, and I is the identity matrices, which will be differently in this case 2 by 2 matrix 0 1 0, and if we put the value of h and subtracting from this, so it will give ln determinant of lambda minus I, this is equal to 0. So this will give us lambda square minus 1 is equal to 0. We will obtain the two eigenvalues, lambda 1 is equal to 1 and lambda 2 is equal to minus 1. So if we apply count this epsilon which was taken out, so it will give E1 is equal to E naught into 1, and similarly for E2 will be equal to E naught minus 1, mean E naught. Okay, so this is the two eigenvalues we obtain. E1 is equal to E naught and E2 is equal to minus E naught. Now we will solve it for the probabilities. To answer the what probability would it have if we have to find the eigenvector for this, we will definitely, if we want to find the probability, we need to find its eigenvector for each state. So for the first eigenvalue E1 is equal to 1, so if we want to find its eigenvector, Ax is equal to lambda into x. X is some unknown vectors which contain x and y entries, and this is the eigenvalues lambda, which is equal to 1. If we apply a similar methods, so it will give us minus iota y is equal to x. We have two equation and two unknowns, so we can find its h1 is equal to x and iota x. At this point we don't know the values of x, so we can obtain it by normalizations condition, because we know that h1 bra and h1 ket should be equal to 1, because this is the requirement of normalization, so h1 and h1 should be equal to 1. Okay, so h1 is given, ket is given. If we take its bra, so definitely that will become a row vectors corresponding to this, and multiply both, this will give us x square plus x square is equal to this, and this will give x is equal to 1 over under root 2. Okay, so substituting using this value in this equations, this will give us h1 is equal to 1 over under root 2 1 and iota. Because we have two eigenvalues, so we will have two eigen vectors. So for the second, if we repeat the same procedure for the second eigenvalues, which is minus 1, so this will lead us a operator a sorry ax is equal to lambda multiplied by x. X is some unknown matrices which is represented by xy. A is the given matrices, lambda is the eigenvalues, and xy. We apply the usual methods. Multiply this matrices with this, and similarly apply multiply this minus 1 with this. This will give two equations, and this has two unknowns, so this will give h2 is equal to this x and minus iota x. At this stage we don't know the value of x again, so applying that h2 and h2 should be equal to 1. This is the normalization condition. We have got this is the equal to column vector. If we take it bra, so this will be converted into a row vector. Then we will row vector multiplied by column vector should be equal to 1, because this is correspond to row vector and this correspond to a column vector. Okay, is equal to 1. So this will h1 h2 is equal to 1 is equal to x square plus x square. If we multiply this row and this column vector multiplied by its row vector, so it will give us 1 over under root 2, and using this value here this position, so x2 will be equal to this. So probability for E1 is equal to psi and h1 whole mod square. So psi is given 1 over under 2 this, and h1 is this, and take its modulus square, this will give us 1 over 2. Similarly, if I center it, probability for the second can be calculated, because total probability is equal to 1. So for the total probability we can obtain it by two methods. Is equal to 1 minus P1, because total probability is 1, so we have a probability for P1 for energy E1. So if we subtract probability for 1, so we can obtain the probability for P2, because total probability is 1. We have probability for the first state which is equal to P1, so this will the probability for the total P2 remaining state. So P2 will be equal to 1 minus P1, so this will equal to 1 over 2. So far we obtained P1, probability for energy 1, and probability for P2. If I go back to question, so that our questions should be complete. Okay, in the third, next we want to find the average value of energy and the energy uncertainty. We start with average value of anything can be found out by inserting it between the two states psi, h, and psi. So we have first to find h psi, h is given, and we have state at this time. So we apply these two methods. This will give us h psi. So h, if we put it back, so it will become h is equal to 0. So it means the average energy is equal to 0. On the other hand, we have that h square, h square is equal to psi into h square for the finding the average value of h square. So psi into h square is equal to this. So h square will be equal to this. By substituting this back to this equation, so this will give h square is equal to epsilon naught square. So then we have uncertainty relations. Delta h is equal to h square average value minus h whole square average value. So as this is equal to 0, so h square is equal to epsilon naught square. So delta h is equal to epsilon naught. Okay, I think to this point our problem is complete.